Hello, welcome back to AIT 1102. This presentation is on flow control, and we're going to describe what flow control is. We're going to describe flow control valve characteristics, identify different types of flow control valves, describe the effects of flow control in a hydraulic system, identify your schematic symbols, and identify flow control failures, causes of failures. So back to our presentation, our schematic. So far we've talked about our motors, pumps, directional control valves, check valves, and this presentation is going to be focused on flow control. So what is flow control and what's it do? Flow control is ability to control the flow rate or gallons per minute of fluid flow in a hydraulic system. It's used to control the speed of actuators in the system. So going back to your mower, your hydrostatic drive lawnmower, you're actually using a form of speed control or flow control with your foot pedal by varying how much you open the valve on that for the drive. You can control how fast you go, so you don't want to go full speed all the time. Flow control valve types, we have fixed orifice and variable orifice valves, and we're going to go through the different ones and kind of show you what the difference is between them all. Fixed orifice valve is much like what you see here. There's no adjustment to it. It's just basically has a port through it, and it's got a restriction inside to a set amount, so as to restrict the flow. Slow it down through this narrowed area. So I mean, it's just a fixed orifice, and this is not exactly how they're made inside, but this is just more or less to give you an idea of what it is. It's just just a reduced flow path. Variable orifice. First type we're going to look at is a globe valve. It's from your textbook. Globe valve. This is going to be very similar to what you might find in a faucet in a house, in a bathroom or kitchen. It's got like a pliable disc or rubber disc that seals against an orifice seat and seals off flow. So here you may have flow to this point, and if this is screwed all the way down, it's sealed, and when I open this up, it pulls this up off the seat and allows the fluid to flow. Gate valve. These are used to on outdoor faucets and hydrants and things. A lot of times they're used to gate valve. But this is the same type of operation. You rotate the shaft like you're turning a knob, and shoves this blue piece right here is the gate. So flow is blocked from getting to right here. So if I open this up and pull this gate up, it's going to allow fluid to flow through this area, and depending on how much I open this gate, depends on how much flow is allowed. The ball valve. These are something you'll typically see more in industrial settings. It's basically a two-position valve, or it's not where you keep turning it. It's just you don't give it a full rotation. Normally it's about a quarter rotation. So I've got a ball here, and through this ball there's a hole through this ball. So when I turn it sideways, the hole is facing this way and is taken out of the path of the opening, and it'll actually block flow against the side of the ball. And if I rotate it, then I rotate the ball, the opening in the ball, into the flow path, and allows the flow to go. Actually, allows the flow to go this way. It's just the direction of flow on this diagram. It doesn't matter which way the fluid flows through a ball valve. And like I said, there's just a hole in here, and depending on which way you can take a hole out of the path and put it into the path. Needle valve. This is what you'll typically see in a hydraulics setting or hydraulic system. It's a needle that comes down here and seals off against this little seat. And depending on how far I open this up, is how much fluid is allowed through this orifice. So if I run this all the way down, I could actually seal this off and stop all flow, and then start opening up and start allowing fluid to flow. So that's the different types of variable orifices. And then the last type is you throttle in a DCV, and this is like what I talked about with your lawnmowers with your hydrostatic drive. You can just move this just a little bit, allow just open up just a little bit of an area, allow a little bit of fluid to flow, or you can push it all the way and open it up all the way and get full flow. So just the different methods to control the amount of flow flowing through a valve. Effects of flow control. So basically what it does is it restricts flow through a system. It's used to control rate or actuator, the flow rate or the actuator speed. So using your lawnmower as an example, you have hydraulic motors on the wheels of your hydrostatic drive lawnmower, and you're controlling the flow to control the speed of those motors are spinning and control the speed of the lawnmower. So when you restrict the flow and control the flow, you create a pressure differential across the restriction. So the greater the pressure differential, the more flow you'll have. And we're going to delve into this just a little bit, just to kind of get a better understanding of what's happening with flow control. So just to give an example, so what is the flow through a flow valve? If the inlet pressure is 2,500 psi, the outlet pressure is 1,000 psi, so that's our pressure differential. If the valve will flow 1 gallon per minute at 150 psi, so we've got this valve, this is our valve adjustment. We've got a needle valve adjusted where we're allowing 1 gallon per minute at 150 psi. So here's our formula. First thing we need to find out is our pressure differential. So to find our pressure differential, we take our pressure before the valve to our pressure after the valve. Our pressure before the valve is 2,500 psi. Our pressure after valve is 1,000 psi, so that's going to give me my pressure differential. So if I just do the simple subtraction, that tells me my pressure differential across this valve, or flow valve, is 1,500 psi. So there's 1,500 more psi on the inlet than there is on the outlet. So back to our example, what is the flow through a valve? If the inlet system pressure is 2,500 pounds and the outlet pressure is 1,000 psi, how much flow will flow through the valve if it's adjusted to flow 1 gallon per minute at 150 psi? So now we have another formula. VQ is our volume or flow through the valve, and we define that. We take our pressure differential and divide it by our pressure to flow 1 gallon per minute. So if I take my 1,500 psi, which is my pressure differential, and divide it by my the pressure it takes to flow 1 GPM, I can determine how much flow is flowing through that flow valve. So at this pressure, I'm flowing 100 gallons per minute through that flow control valve. So you can see that there's three things that has the impact the flow through a flow control valve. The inlet pressure, or the pressure differential between the inlet and the outlet, and the set and adjustment of the flow control. If I change any one of these three, it's going to change how much flow is flowing through that flow control valve. So if I open my flow control valve up, I mean, it may take only 100 psi now to flow 1 gallon per minute, which would have an impact on our overall flow. So let's just say I did that. So I opened my valve up, so I gave it more room to flow through the needle. So now I'm flowing 1 gallon per minute at 100 psi. So if I plugged it and if I pressure stay the same on the in and out, so if I take this and divide it by 100 now instead of 150, I'll be flowing 150 gallons per minute just by changing that adjustment. Or if I change the pressure on the input or pressure on the output, will also have an impact on that the amount of flow through that flow control valve. So if you can play around with that with these different formulas. The textbook goes into this a little more in depth, but I just wanted to go through one of these examples with you just so you had an idea of what we're talking about here when you go through the material. So another type of flow control valve, all the ones we've looked at before, like I said, these different pressures, anything could have an impact on that, the pressure and the flow has a big impact on flow. So what if we have a situation where we don't want the pressure to impact the flow? So we come up with a pressure compensated flow control valve. So you can see that this is a little more involved than just a straight orifice or needle seat. So what I've got here is my system's coming in here, and I'm allowing it here to flow to my regulated flow, so I'm controlling the flow coming out of my output here. So let's say I've got 1,000 psi here and 500 psi here, and I've got a setting here, so that's going to generate a certain amount of flow through that. So let's say I change this to 250 psi, but I want to maintain the same flow through this valve. By changing the flow, or by changing the pressure on my output, allows this spool to move against the spring. Because if you see my pressure, my inlet pressure here is coming in here and going out through this flow control, but if my pressure here drops, where I've got my system pressure coming in and pushing on this spool here, if this pressure drops, it's going to allow the spool to shift up, and it's going to start closing off more pressure. Or the same thing happens if I increase the pressure here and I want to maintain my flow. So if there's more pressure up here, it's going to shift this spool down and allow more flow through here. So by having this moving spool in here, I've got a balanced load where I've got my system pressure here and my regulated pressure here. And as the pressure changes, the spool shifts to compensate for those changes in pressure to maintain a constant flow. So just another type of flow control valve. You notice this one over here has got a check valve in it. So that tells me I'm controlling the flow going out to my load or whatever it is. But when the flow is coming back, I've got a check valve here that opens up, allows the flow just to go. I won't be controlling the speed of the flow coming back. It'll give me full flow. So we've talked about flow control. Now it's where do we put these flow control in a hydraulic system? There's two primary types you can do. You can do meter in and meter out, and I think this was probably discussed in 2003 when you were looking at speed control. But just kind of a review as to what you learned in AIT 1003. So I've got a hydraulic cylinder here. It's a double acting cylinder, so I can put pressure on if I shift my valve here, put pressure on the rod end or the cap end or the blind end. So I'm putting pressure here. I'm allowing this one to go back to tank. So my fluid is flowing in this direction from A to B. So when I'm controlling the fluid going into my actuator, that's a meter in. I'm metering the fluid flow going into the actuator. And I'm doing that by the fluids coming in here. This check valve is, see the direction it's pointing. So I'm seating the ball, so this is sealed off and forcing all my fluid to go through this needle valve here where I'm actually controlling the flow. So I'm controlling the extend speed of this cylinder. So if I shift my valve the other way and put pressure on the rod end and allow the cap end to go back to tank, so the fluid's coming in here, so the fluid will start leaving here, so the fluid will go through here, but it'll also unseat the check valve and give me full flow, so it'll retract faster, at a full speed versus the controlled extend speed where I'm metering the fluid coming in. Meter out is just the opposite. Instead of metering the fluid going into the actuator, now I'm metering the fluid coming out of my actuator. So if I shift my valve this way, put pressure here and allow, so I'm filling this end of my cylinder with pressure. This fluid is running back to the tank. So it comes down here, tries to go this way, but I've got a check valve, so I'm closing that off, and all the fluid leaving here is forced through my flow control, going back to tank. So I'm slowing this fluid leaving the cylinder and actually controlling the speed. And different applications, typically you do meter in, like when you have a horizontal load, where you don't have anything, gravity or anything with a load acting on the cylinder, and meter out gives you a little more control on a vertical load. So if I've got the cylinder was pointing up and I've got a heavy load on top of it, the meter out gives me a little more control. If something happens and my valve fails and starts allowing fluid to flow, the meter out would actually slow the descent of that valve. You can use them meter in, meter out in different applications, but that's typically how they're used. Schematic symbols for your fixed orifice, for your flow control. This is a fixed orifice flow control. You can see the symbol here just shows it's a restricted area as the flow goes through. And there's no adjustment here. Everything just shows that orifice restricts the flow a set amount. And again, you see my angled arrow. That tells me that this is adjustable or a variable flow control valve. So much like on your hydraulic pumps, I have a fixed displacement pump that had no arrow. Same thing with my orifice, fixed displacement, no arrow, or variable. I have the angled arrow across the symbol. Flow control with integral check valve. We've been seeing these. So this is what you'd use on like your meter in, meter out. So when the fluid's flowing this way, I've got a variable orifice here, or variable flow control. So when fluid goes this way, I seal my check and forces all the fluid to go through my flow control so I can control the speed. Fluid comes back this way, pushes my check open, and allows full flow through here, and I'm not controlling the speed when the fluid's flowing back this direction. Another symbol, so this is my flow control with the integral check with this sideways arrow in line with the flow control. That tells me that this is a pressure compensated valve. Like it would show if the pressure on either side changes, the spool inside that pressure compensated valve will shift and maintain the set flow. So again, we're talking about this section here. So I've got my pump putting fluid into the system, and I'm got my DCV here. If I shift my valve, so if I shift it this way and put my P port to my A port, that's going to allow full flow to retract the cylinder, because when fluid's flowing this way, it's going to push the check valve open, allow full flow here, and this fluid going back to tank. I shift my valve the other way, so now I put pressure on my B port and allowing my A port back to tank. So when I pressurize this end of my cylinder, filling fluid here, the fluid's leaving. It's checked this way, and fluid is coming all through my flow control, and so this would be a meter out arrangement. Causes of failures, again, if you're noticing a theme here, contamination. Contamination is one of the worst things you can have in a hydraulic system. If you clog orifices, because some of these orifices are kind of small, so very much contamination. You can clog an orifice and not allow any flow through that flow control. You could get stuck or dragging spools like in a DCV on a pressure compensated valve. You can create internal leaks on check valves. Like I said, if you get contamination on the actual seat, it could not allow the ball to pop it to seal off all the way and not control the flow. You can have mechanical failure. Maybe the orifice inside came apart and cracked and it's not controlling the flow anymore. The valve body could possibly crack. You could have a wore orifice, a needle and seat, have loss of control, drifting of control, where you can't control the speed. I mean, sometimes it'll seal off good, and sometimes it won't, and you'll have a loss of control. Fluid temp outside of operating range is a possible. It's not necessarily a damaging effect, but it could have an effect on flow, because as you heat an oil, it gets thinner, and most machines that I've had experience with haven't recommended operating temp on the hydraulic fluid. So they've actually got fluid heaters in the reservoir that heats the fluid to a specific temperature, and it also has a heat exchanger that controls the temperature, so it can monitor and control the temperature of the fluid to keep the temperature at a constant temp. And if your heat exchanger clogs up, and I've seen that happen before, where the water's supposed to be flowing through to cool it, much like a radiator, those tubes in there can get clogged up and stop the flow, and then you're not able to cool the hydraulic oil, and it can get too hot, and it can cause you problems of not being able to control the speed and get your speed control out of range. So that's the introduction on flow control. If you have any questions, post them in the discussion board, send me an email, call me. I'm glad to help answer your questions. Thank you.